Neural networks are wonderful at seeing images, but audio arrives as a long, wiggly line of numbers, and that's surprisingly hard to model directly. So almost every speech, text-to-speech, and music system reaches for the same trick first. It turns the sound into a picture. That picture is the Mel Spectrogram, and today we're breaking down what it is, how it's built, and why it matches the way you actually hear. Let's actually build a Mel Spectrogram, stage by stage. First, slide a short window along the waveform. Instead of analyzing the whole clip at once, you look at tiny overlapping snippets, each just a few milliseconds long, and you move that window forward step by step across the entire recording. Sound changes moment to moment, so you have to study it moment by moment. Then, for each window, apply a Fourier transform. This is the short-time Fourier transform, and it answers a simple question for every snippet: how much energy sits at each frequency. Stack all those answers up side by side, and what you get is a picture of frequency over time, the raw spectrogram before any warping. Next, warp the frequency axis onto the Mel scale. Here's why that matters. Human ears aren't linear at all. We hear fine detail at low pitches and lump high pitches together. So the Mel scale rescales the axis to spin its resolution exactly where your hearing actually cares and less where it doesn't. Finally, take the logarithm of the amplitudes, which is roughly a decibel scale. Loudness, just like pitch, is something we perceive logarithmically rather than linearly. So this last step lines the numbers up with perception one more time and give you the finished Mel spectrogram, ready to use. Now here's the shift that makes this so useful side by side. The raw waveform is a single long line of amplitude values, tens of thousands of them every second. All the meaningful structure, the pitches, the phonemes, the melody is tangled up together in that one-dimensional squiggle, and pulling it apart is genuinely hard, which is what makes the waveform awkward to feed a network directly. The Mel spectrogram unfolds that squiggle into a compact two-dimensional image. Time runs along one axis, Mel frequency bends along the other, and brightness shows how much energy is present. Suddenly the structure is visible on the page, and it's matched to how you actually hear, so a neural network can read it much like a photo. Let's pull out the three ideas that make the Mel spectrogram so handy. The Fourier analysis is the engine, applied to short windows one after another. In what's called the short-time Fourier transform, it gives you time along one axis and frequency along the other, turning a flat signal into a rich two-dimensional map. The Mel scale is what makes it perceptual. Warping the frequency axis to match human pitch perception means the representation emphasizes exactly the details our ears find meaningful and compresses the ones we barely notice, so the network spends its capacity on what matters. Looking like an image is the payoff. The result is a clean two-dimensional array you can hand to a CNN or a transformer, just like a photo, which is why it's become the standard input across speech recognition, text-to-speech, and music AI. Okay, let's lock in the essentials. The Mel spectrogram turns audio into an image of frequency over time, and it's become the standard input for audio neural networks everywhere. The Fourier step, applied to short, sliding windows, reveals how energy spreads across frequencies over time. Warping the frequency axis to the Mel scale matches human hearing, and a final log step matches the way we perceive loudness. The finished array feeds a CNN or transformer just like a photo, and text-to-speech models predict it, then convert back to sound. Hungry for more AI concepts made clear? Standarity.com is where they live. Catch you there.